Hello folks, so this is the second video I've done on discrete random variables. If you haven't seen the first video yet, then do make sure you go back and watch that first. This one is going to cover finding the expected value, variance and standard deviation of functions of discrete random variables. Okay, so we're going to start just with a bit of practice. So there's a try this part here. If you could just have a go at finding the expected value, the variance and the standard deviation for the probability distribution given here. So just pause the video, try that, and then we'll check your answers. Okay, so hopefully you managed to get these results here. It might be that you've learned how to do this on your calculator. By all means, for this next exercise, do feel free to use your calculator to speed things up if you want. Because what we're going to do now is try and find the expected value, the variance and the standard deviation of each of these functions of x, where x is the probability distribution that we started with at the top. So for example, for part A, we could write out a new probability distribution function with our values of 2x along the top. To find the expected value of x, we multiply each value by the probability and sum them, so we get 4.8. To get the variance, we'd need to first find e of x squared, so we square each value of x and multiply it by the probabilities to get 24.8, and then use the variance formula to end up with 1.76. Okay, the standard deviation we know is just the square root of that, so that comes out to be 1.33. So in your video pack you've got this table. So the first column is just going to have the values of e of x in it. The first one there we've just got for 2x, we got 4.8. Second column is the variance, and third column the standard deviation. Okay, so again, if you can just pause the video, have a go at trying to do exactly the same for these other functions of x. Okay, so hopefully you ended up with these results here, and as well as a bit of practice, the reason for doing this was because you might have already spotted there are some relationships between our original values and the new values for the expected value, variance and standard deviation. So if we start with the expected value, our original expected value was 2.4. When we found the expected value of 2x, it came out to be 4.8, and you might spot that this is indeed just double that value. So it seems like we can just double e of x to get the e of x when it's 2x. For this one, we added 3 to each value, and well, you can see there we've just added 3 to the expected value. This one is a mixture of the two, so indeed if you double this and then add 3, it does come out to be 7.8. I'm just going to leave D for a minute. If we go on to E, then it seems like exactly the same has happened. -5 multiplied by this does give us -12. If we subtract 1 from this, we do get 1.4, and then a mixture of the two, multiply e of x by 5 and then subtract 1, you get -13. So for these functions, a, b, c and e, f and g, there seems to be an easy rule there, or a set of easy rules, but this one is different. This is a non-linear function, all the others are linear, and it should be noted that this value of 6.2 is definitely not that squared. So for non-linear functions, these simple rules don't seem to follow. Okay, I'm going to look at the standard deviation now, and some similar things seem to be happening. So all of these have been rounded to 2 decimal places, which causes a little bit of a problem, because here standard deviation 0.66, here it's 1.33. Well, in fact this is just double that value, but due to rounding it doesn't look quite right. Okay. However, when we've added 3 to all the values of x, then actually we've ended up with the same standard deviation that we had. So that's a bit different to the rules for the expected value. And indeed for this one, again, the standard deviation has been doubled, but the add 3 has no impact at all. I'll leave D again, and very similar thing seems to happen here. However, standard deviation is a measure of spread. It has to be positive. So rather than negative 5 times that, it is actually just 5 times that. The -1 again has had no impact on the standard deviation, on the spread, and a mixture there, again that -1 has no impact, so it's the same as this one. So it appears that if you double the values of x, then the standard deviation doubles, which kind of makes sense. Now we know that the variance is the standard deviation squared, so if we've doubled the standard deviation to get this, then it kind of makes sense that to get from the variance to the new variance for 2x, we would actually have to multiply by 2 squared, and this is indeed 4 lots of that. Again, when we've added 3 to the data, it's had no impact on the spread, so the variance is the same. This is going to be the same as this one because the +3 has no impact, and similarly down here, that rule seems to hold. So we're multiplying the variance by this coefficient of x squared. Okay. Again, for this non-linear ones, the rule there definitely doesn't seem to hold. So it appears like we've got rules that we can identify for when we find linear functions and only linear functions of x. Okay, so we'll have a look at those rules now. And the first result is that if we find the expected value of a linear function ax plus b of x, then it's simply equal to a lots of e of x plus b. Alright, so a very simple result there. Slightly more complex for the variance because we decided that that plus b doesn't have any impact. So it's simply a squared times the variance of x. There are proofs of these two results here, so I'm just going to put them on the screen. It'd be worth pausing the video, having a look through, and then you can ask me about anything you're not sure of in the next lesson. So similarly here, the proof for result 2, have a look and ask me if you're not sure. Okay, so how do we use this? First we're going to have a look at a kind of graphical image of what's been going on. So this is the probability distribution that we started with at the start of this lesson. So the probability of the values, possible values 1, 2 and 3 were 0.1, 0.4 and 0.5. So the blue bars there are the original probability distribution, and then I've doubled each of those just like we did in part A earlier, so the new values are 2, 4 and 6 and the probabilities stay the same. And hopefully you agree that the mean would perhaps have been around here for the original distribution. When we've doubled it, well, it's jumped to over here, so from around 2 to 2.5 up to sort of 5 and 5.5 there. Okay. The spread also seems to have changed, so here they're spread between these values, here they're twice as spread out, so the standard deviation has doubled. Okay, but because the standard deviation is the square root of the variance, or the variance is the square of the standard deviation, we know then that the variance would have to go up by the 2 squared, it would be 4 times as big. If we look at adding instead, so here again we've got the original values of x and then the values of x plus 3. And again we can see that the mean does seem to have moved 3 further up, so we're adding 3 to the mean, but this time the spread hasn't changed at all. So that's why when we add something to the values of x, then the standard deviation and the variance don't change. So hopefully that just helps you visualize what's happening. Okay, so how do we use it? So an example here, random variable y has a mean 5 and variance 16, which we've been given, and we're asked to find the mean and the variance of these two. So for part A, it's 2y, so the expected value of that is just going to be 2 times the expected value of y. So 2 times 5, which is 10. And for part B, for the variance of part A, well, we have to remember that if we find the variance of 2y, then that's equal to 2 squared, or 4 times the variance of y. So 4 times 16, in this case 64. Part B, if we're finding the expected value of 3y minus 8, we do 3 lots of the expected value of y, and then we subtract 8. So that gives us 7. And for the variance, we just have to remember that the minus 8 has no effect at all, so it's simply 3 squared, or 9 times the variance of y. So 9 times 16, 144. As usual, try this part here, so it'd be worth giving this a go. We're given a probability distribution, this time in the form of a formula or an equation or a function, and we're given the possible values of x there on the right as 1, 2, 3. We're asked to find c, find the variance of x, and then find the variance of 6x plus 2. So you're going to need to start by drawing out a probability distribution and using that to work out C, and then you should be able to do B and C. So pause the video, have a go, and then see how you've got on. Okay, so for this one, probability distribution, when we draw it out, we get this table here. Clearly we could have written C over 1 here, but C over 1 is just C, so we can just write that. We know that the probabilities have to add up to 1, so if we use that information, then we should end up with C equaling 6/11. Probably worth redrawing the table with the probabilities in it, so that's what I've done here. And to find the expected value of x, we do the normal multiplication of the values and their probabilities and add them up. Do the same to get e of x squared, and then use the variance formula to find the variance. Not asked for the standard deviation this time, so we don't need to do that. Then for part C, we could do it all again by writing the values of 6x plus 2 along the top, but in actual fact we've got a rule now that we know works for linear functions, so we can just take our original variance and multiply it by 6 squared, or 36. So that comes out to be 21.4. Okay, so hopefully that has helped you to understand how we deal with linear functions of discrete random variables, and you'll be able to have a go at some questions in the next lesson. Okay, thanks, bye-bye.